Now, the thing I really want to emphasize here is the only change we're making is breaking off the carboxy group. So how many carbons should we be losing? Only one carbon. A mistake that I see people make is a lot of people would also blast off this carbon. Don't blast off this carbon. We should don't blast off the alpha carbon, only the carboxy carbon. Only blast off the carboxy carbon. When you look at the mechanism, you'll see why that's right. But for now, we'll just memorize only blast off the carboxy carbon, not this alpha carbon. Notice how this number 3 alpha carbon is still here. What happened to this number 4 carbon and these 2 oxygens? They got turned into carbon dioxide. By the way, what happened to this hydrogen? It went to
alpha.
Good, it went to the number 3. Maybe not the same exact hydrogen, but anyway, this has gained a hydrogen, because this has 2 hidden hydrogens, and this has 3 hidden hydrogens. You don't need to draw that, but that accounts for all of these atoms over here. All right, so just break off the carboxy. Don't do anything to the alpha carbon here. And look for beta carbonyl carboxylic acid, and all this takes is heat. We don't have to add any other reagents. All we need is heat. Okay, you should practice that, but I don't want to spend more time on that now, because that's in the other video series too. So we'll just see how we can use this. Let's talk about what would happen here. Let's actually propose this out loud. Any suggestions about what would happen first here? Okay, yeah, let's keep describing. All right, actually, let's not go through the whole mechanism. Well, we can. Also, what major reaction is going to happen here first?
You're going to form carboxylic acid.
Right, perfect. What's the name of that reaction?
Hydrolysis.
That's right. We know that this is a carboxylic acid. What type of functional group do we have on the right over here?
Ethyl. And ester.
And ester. Yeah, sorry, we have an ester. Well, we know that esters can hydrolyze under either acidic or basic conditions. So we'll do a acid-catalyzed ester hydrolysis. To save time, let's not draw the mechanism. Let's just draw the product of that hydrolysis step. Let's just write down what the product of that hydrolysis step will be. Good. Okay, it's very easy to write the product of hydrolysis. We know that water is going to replace this leaving group, but we know that it's eventually going to deprotonate, so it'll be an OH. All right, we haven't gone through the whole mechanism for that here, because we know how to do hydrolyses. And of course, there would also be an ethanol leaving group, but I'm not going to bother drawing that. Now what would happen? Oh, I'm sorry, let me interrupt you. By the way, there is a reaction whereby water can attack ketones, but that is not a very favored reaction. That generally favors the ketone, and that forms what's called a Geminal Diol. But the Geminal Diol is not really favored in that reaction. We get mainly the ketone and not much diol. So we should ignore the water attacking the ketone here. We need to focus on the water attacking the ester, because that gives us a very clear-cut reaction over here. So we shouldn't be drawing the water attack here. Okay, now what?
It's going to do decarboxylation.
That's right, because we didn't just add aqueous water, we also added heat. And we know that under moderate heating, now how do we know this is a candidate for decarboxylation?
It's carboxylic acid. Beta carbonyl
right.
carboxylic acid.
Not just a carboxylic acid, but a beta carbonyl carboxylic acid. So let's draw what the final product would be. And again, we won't go through the mechanism. Let's just draw that final product. Okay, all ready? Good. Excellent. This is the same reaction we were just looking at. Good. Okay. Now, this is something that you can do then with 1,3-dicarbonyls. What can you do with 1,3-dicarbonyls? Well, if they have a carboxylic acid derivative, like an ester, you can hydrolyze them to a carboxylic acid, and then once you hydrolyze them, they can decarboxylate. Now, by the way, notice that this is only one step as far as putting in the reagents. You don't have to say 1 and then 2. You just say H3O plus, comma, heat, and then all of this will happen. This is very frustrating to students because they tend to stop too soon. A lot of people get this far and then they congratulate themselves and go on to the next problem. They don't realize that the heat is going to do the decarboxylation. So you need to do a bunch of practice problems and get frustrated with that a couple of times until you start remembering to look for decarboxylation reactions. So watch out for these. Anytime you formed a beta-carbonyl carboxylic acid, watch out for decarboxylation. What would be the product of this first step here? Let's just talk this out in words. What happens when this starting material reacts with this?
Enolate.
It's not a bad guess. What else might happen though? What could this do besides making an enolate? Right. As a nucleophile.
Yeah.
What would we call that reaction where this attacks as a nucleophile? What would our product be? What type of reaction? I'm sorry? That would be if we, not when we're attacking a carbonyl.
Then we made a carboxylic acid.
So it would be hydrolysis again. It would be base catalyzed hydrolysis. A second ago, we had an acid catalyzed hydrolysis on the board, but these are the reagents for a base catalyzed hydrolysis. Except remember that we wouldn't make the carboxylic acid, we'd make the carboxylate, because under basic conditions, carboxylic acids deprotonate. Did we ever talk about that? Or I don't know if you've seen that in class. Under basic conditions, carboxylic acids deprotonate. So step 1 would give us something that looks like this. These are good conditions for a base catalyzed hydrolysis. So step 1 would be this. And then what would be the effect on this compound of adding these reagents?
Protonate the O- and then decarboxylate.
So we would still get the same product as before. So a few minutes ago, I showed what would happen if you just added H3O plus and heat. Well, that would be acid catalyzed hydrolysis followed by decarboxylation. And here we showed how you could do a base catalyzed hydrolysis followed by decarboxylation.
So why would you want to do it base catalyzed if you still need to use the acid? Any, like, is it just easier?
That is an excellent question. I've never figured out the answer to that. If you're going to have to add H3O plus and heat eventually anyway, why bother with the base catalyzed hydrolysis?
If you add H3O plus and heat to begin with,
yeah,
you get the protonated.
Yeah, absolutely. So, and usually you do prefer the shorter syntheses, but for some reason the book always covers this as well. There might be some advantage. There must be some advantage, but I don't know what it is. There must be some advantage, but if you're gonna have to add this eventually anyway, I don't see what the advantage is. But anyway, this is also a common reaction in the book. But you're absolutely right. All right, so we should know that you can either do the acid catalyzed hydrolysis and then heat, for decarboxylation, or base catalyzed hydrolysis, which gives us the carboxylate, and then we can add H3O plus, which protonates this and then gives us the decarboxylation. By the way, this cannot decarboxylate until it's protonated. Only beta-carbonyl carboxylic acids can deprotonate, not beta-carbonyl carboxylates. Beta-carbonyl carboxylates can't deprotonate. That's no big problem because it's very easy to protonate this and then it can decarboxylate. Okay, so I don't know why you would ever want to use the base catalyzed method as opposed to the acid, but it's in the book. That would be a good question to ask your TA because I always wondered about that myself. So.